When we graph x cubed, we get the curve shown here. When we graph the line 15x plus 4, we get the line shown here. When we graph the curves in one panel, we see that they intersect at the point where x equals 4. This means that the equation x cubed equals 15x plus 4 is solved by x equals 4. We have a real solution to the equation. There is a formula that says that when x cubed equals 3px plus 2q, the solution is x equals the cube root of q plus the square root of q squared minus p cubed plus the cube root of q minus the square root of q squared minus p cubed. In our equation, we get 3 times 5x plus 2 times 2 on the right side of the equation, so our p is 5 and our q is 2. If we plug in our values of p and q into the formula and simplify under the root symbol, we get our value of x to be the cube root of 2 minus 11i plus the cube root of 2 plus 11i. So how do we reconcile the result from the formula, which involves the cube roots of complex numbers with the real value of 4 from the graph? We're going to assume that the cube root of 2 minus 11i can be written as 2 minus ni, and the cube root of 2 plus 11i can be written as 2 plus ni. This is an assumption made by Bombelli a long time ago during the initial struggles to understand complex numbers. This is a useful assumption because when we add 2 plus ni and 2 minus ni, we get 4, and the parts ni and negative ni cancel to leave us with only 4, which is the same as the real value of 4 from the graph. We can cube both sides for the cube root of 2 plus 11i. We have to now assume that we can expand 2 plus ni to the third using the usual rules. Place yourself in the mindset of a person living hundreds of years ago. None of this was obvious. To this day, we often just assume something, using our intuition and hope, and see what comes of doing so.
Recall that x plus y, quantity cubed, is x cubed plus 3x squared y plus 3xy squared plus y cubed. We can apply this pattern here too.
Using this pattern, we get 2 cubed plus 3 times 2 squared times ni plus 3 times 2 times the quantity ni squared plus the quantity ni cubed. Simplifying the expanded expression using various powers of I and gathering the real and imaginary parts, we get 8 minus 6 n squared plus 12 n minus n cubed I. We can now set 8 minus 6 n squared equal to 2 because both represent the real parts. Equating 2 and 8 minus 6 n squared and solving for n tells us n is 1 or negative 1. Replacing n with 1 in 2 plus ni and adding gives us 2 plus I plus 2 minus I, which is the 4 we were hoping for. You have now seen a little of the history of complex numbers. If you learned something in this video, please be sure to leave a like. A book you should check out is called Visual Complex Analysis by Tristan Needham. It's full of amazing illustrations. Link is in the description below.